In this example, we're going to consider a block sitting on the ground, one of the greatest examples in all of physics. Blocks for everyone. And the coefficient of friction between the block and the table will be 0.41 in our example. Just so you know, this number always comes from whatever the two objects are made from. So it's unique to the situation. Well, that's a little strong. Like if I have cardboard, like my notepad, put on my notepad on the wood table, there's a coefficient of friction for cardboard on wood, and you just go to the big book of coefficients of friction, or Wikipedia, and you pull off the number. We're going to put a force on this block in the horizontal direction of 400 newtons, and then ask the question, how fast is the block moving after it's been pushed 6 meters? So just trying to find a way to notate v at 6 meters is what we want to find. And there is a way to do this by figuring out what the net force on the block is, and then figuring out what the acceleration is from that, and then figuring out what the velocity is at 6 meters. And you could do that with kinematics. We could start working through a couple kinematics equations and figure out how we get v in terms of x and a. Or we can do this from an energy perspective. And often problems that you can do in kinematics, particularly if they involve just one dimension, and sometimes, well, so problems you can do in kinematics can often be made easier from an energy perspective. And if problems involve 2 dimensions or 3 dimensions, and they start getting really messy in kinematics, it often turns out that they're easier to do with energies. So let's do this with energy. We know the block is going to go 6 meters, and we know we have a pushing force on it of 400 newtons. So what I want to do is I want to figure out how much energy the push puts into the system and how much energy friction takes out. So I want to find the total amount of work. And you had a WebAssign problem that showed you could do this by either finding net force and then multiplying by your distance, or by finding the two works and subtracting them. But once I found the total work, I want to use something called the WorkKineticEnergyTheorem. And it has a fancy name, but all it means is my total work is equal to my change in energy. In this case, my total work is equal to the change in kinetic energy. If the block starts from rest, this is easy because my initial kinetic energy is 0. So if you think about what's hiding inside that delta, is K kinetic energy F minus KE I. This number is 0, so my delta, or change in kinetic energy, is just my final kinetic energy. I'm not sure, and I'll try to look before the next round of videos, what your book uses as kinetic energy. It might call this T. Not sure what their convention is. It kind of goes crazy. But I'm just going to say KE for now so you can see clearly it's kinetic energy. All right, so I need to find the work, and I'm going to do it in 2 parts. First, I'm going to find the work from the push, so just that thing, 400 newtons. And for that, I just do force times distance, because there is no angle here. The push and displacement are parallel. So if you've come to the tutorial and talked to me about this, you'll know that if I just have parallel push, or push and displacement, or force and displacement, if those are parallel, it's just force times distance. I don't have to worry, because the cosine of 0 is 1. And 0 would be the angle between them. Alrighty, so that's just 400 newtons times 6 meters, which is 2,400 joules. Right, and then I want to find the work done by friction. So I need the force of friction, the displacement. And from this picture, if the block is going to move this way, friction resists movement, so that means the force of friction will push against and go that way. And so that will mean that my force, in this case, force friction, and my displacement are in opposite directions, and if you come to tutorial and talk to me about that, then you would know that work will be negative here. And the angle between these two would be 180, so if I drew that angle, and the cosine of 180 is negative 1. That's how I know the work will be negative. So I'll just go ahead and plop down that negative in front of it. So now I have negative, and the force of friction is going to be mu times the normal force. And we've done a bunch of examples like Fn times d is going to be negative 0.41, 200 newtons, 6 meters. And when I do that out, I get that that is negative 492 joules. So my total work, as the name implies, I just add up 2,400 joules and negative 492 joules. When I add up those two numbers, I get 1908 joules, 1,900. Ooh, that's really sloppy. 1,908 joules. And now that, by the work kinetic energy theorem, and the fact that we had zero kinetic energy, we weren't moving at the beginning, is my final kinetic energy. Well, that doesn't seem like it answered the question, right? We want the final velocity. The whole point of this is that I know kinetic energy is 1/2 mv squared. And if I want to talk about my final kinetic energy, I just put a final on the kinetic energy and the velocity. And so now I have this, and I can solve that equation for v. So 2 times my kinetic energy over the mass under the square root. 2 times 1908 joules over, we said the block was 20 kilograms. And when I do that arithmetic, I get the velocity is 13.8 meters per second.